Okay, thank you, Paolo. Thank you very much for the invitation. It's really a pleasure to be here and to give a talk to the Financial Computing and Analytics Group. The title of the talk is basically a network view of cryptocurrencies with a focus on Bitcoin Lightning Network. Actually, I would like to be a bit more general and provide also some overview of recent results about Bitcoin, the proper Bitcoin. And by doing this very simple introduction. So in how many ways can we approach the study of cryptocurrencies? Well, here at IMT Lucca, at least from three different perspectives. There is a proper economic one. So people from economics are interested in, for example, understanding if there is a strategic behavior of users joining cryptocurrencies, or from a purely from the perspective of computer science. So people working in the area are interested in the algorithm that make the blockchain work. And then there is the third view, which is the view of a complex scientist, or complex system scientist or network scientist, as you prefer, which is my perspective. And I'm interested in building networks out of data about cryptocurrencies and see how the analysis of these networks can help us in understanding cryptocurrencies. Recently, there has been a huge wealth of literature about this approach, and actually trying to combine the results that come from a purely structural analysis of these networks induced by cryptocurrencies data, together with the economic perspective. So let's say trying to understand if the analysis of the topology of the network can give us some insight on the presence of some strategic behavior, for example, or some movement that then is reflected into the price, for example, of Bitcoin. Okay, so let's start by providing an overview of the results about Bitcoin. Summing up what is how it works. Basically, it is based on the blockchain. The blockchain is nothing else than a sequence of blocks. Each block is a list of addresses, actually of pairs of addresses. The first one indicating the sender of the money, the second one indicating the receiver of the money. So how can we build the networks out of this blockchain? Well, a very first intuitive representation, I would say, is the Bitcoin address network. We use this name in a recent paper, and the idea is that nodes are the addresses, and the links basically connect any two nodes, so any two addresses, if there is a flow of money from the sender to the receiver. So we have a binary directed network. If you add the information on the amount of money exchange, it's a weighted network, but the philosophy is this one. There is another coarser grained representation of Bitcoin data, which is the Bitcoin user network. In this case, users must be understood not necessarily as persons. They are entities that own one or more addresses, and that you can collect together by using what are called heuristic technique. So there are, yes, heuristics. I mean, they are based on some regularities that are observed in the blockchain, and that let you imagine that there are groups of addresses owned by the same entity. So we call users these entities. So the nodes become these clusters of addresses, and the links are put between the clusters of addresses as soon as there is a link between the underlying addresses, the addresses that constitute the users. Okay, so given these two representations, we analyzed the evolution of these two networks at different time scales, daily and weekly time scales. Actually, it doesn't change much. The behavior of these for different representations is basically the same, because it's Bitcoin address and user network at both daily and weekly time scale. So the picture is basically the same. There is a system that is growing, so the number of nodes is rising. The number of links is rising as well. However, the link density is decreasing. So the network is becoming larger, but it also becoming sparser. And the mathematical law with which the density decreases is actually very simple. I mean, we found it to be very well described by this kind of power law 1/n. Since the link density is actually the average degree divided by n, this means that the average degree remains constant, or let's say bounded throughout the Bitcoin history, which means that on average, each node has more or less the same number of connections, and it remains stable through time. Now, this average number of connections is actually very small, in some cases 1 or 2. So what does it mean? Well, we imagine that the system is growing according to a mechanism which is very, let's say, that recalls the preferential attachment mechanism. So there is a new node joining the network and establishing, let's say, one connection with a very well-connected node in the network, a hub in the network. So if we imagine that the new node is a user, we also can imagine that the hub is, for example, a market exchange. So the user buys some Bitcoins, for example, and keep them aside, and that's it. I mean, that's the activity that we imagine that the user can do. So in this sense, it is not still used as a widely adopted way of payment, if you want. This kind of growth induced by the preferential attachment that has been proposed with different with a pair of variations in the literature would also explain, would also account for the this kind of degree distribution, which is very reminiscent of power law degree distribution. To be precise, we can just say that this degree distribution is, let's say, fat-tailed and not precisely power law, because we did the Kolmogorov-Smirnov test. So we tested the hypothesis that degrees are power law distributed, and we can't always say that the null hypothesis is not rejected. So let's say that there is evidence for almost half of a snapshot that the degree distribution is compatible with the power law. However, not always from a purely mathematical point of view. However, the functional form is still compatible with the interpretation of the presence of 1, 2 big hubs together with many nodes with a very small degree. The interpretation remains the same. Okay, what about the mesoscale structure of Bitcoin? Well, at the mesoscale structure, we found evidence of a bow-tie structure. The bow-tie structure is a kind of core-periphery structure. So you have a core of nodes which constitute the SCC, strongly connected component. And the characteristics of this core is that you can always find a path from one node in the core to any other node in the core. So there is always a path between any two nodes in this central component. And then there is the periphery, if you want, which is made by the in and the out component. In the in component, you have nodes that point towards the core. In the out component, you have nodes that are pointed by the core, the central portion of the network. And we found evidence of this bow-tie structure, let's say, especially in a period of 3 years, from 2013 to 2016. In that period, you have a quite large core, which is larger than the peripheral part. So in these 3 years, you have the usual picture provided by a bow-tie structure, which is schematized here in this slide. And then after 2016, this picture becomes less clear. So the core portion seems to shrink and the periphery seems to enlarge. So it's not that clear. Okay, I would like to skip this and move to the Bitcoin Lightning Network, which is, it is defined as a second layer network or second protocol of the Bitcoin, of Bitcoin, that has been developed to try to overcome one of the limitations of Bitcoin, which is scalability. So the rate at which blocks appear in the blockchain is not that large, let's say. Bitcoin is not still competitive with traditional ways of payment. So developers have thought of an alternative way of making, of exchanging money, which is via the Lightning Network. The idea is that there are users that basically have channels open between them, and so payments move through the channels. So in this case, you have a proper network to study. You don't have to imagine fancy ways of defining a network. You have those channels, and a user that want to make a payment can have an up-to-date view of the network by looking at the routing table. So he sees which are the channels open between nodes and can choose to move money across the nodes to reach the receiver. So in this case, we studied this network. Okay, so what we found, basically the number of nodes is still rising. There was a period of time where the rise was quite steep, followed by a period where there is a kind of decrease or less steep increase in the size of the system. The total number of links still rises, as for traditional Bitcoin. However, the link density still decreases. So the network is becoming larger, is becoming sparser. If we plot the density in a log-log scale, we see this red dashed line that still represented the power law n raised to the power of -1. So still there is evidence of a period where this law seems to indicate that the density decreases with an inverse proportionality with respect to the number of nodes. Okay, what about the degree distribution, strength distribution, and weight distribution? Because the Lightning Network was studied also by accounting the amount of money exchanged. Well, for what concerns the degree distribution, so the number of the distribution of the number of neighbors of the nodes, here the Kolmogorov-Smirnov test tells us that these distributions are indeed compatible with power laws. So we have nice evidence of that. For what concerns the weight and the strength distribution instead, here there is something that characterizes many other economic systems. For example, the world trade. In the world trade, you see the same if you plot the weight and strength distribution, and you see that they are more compatible, let's say, with the log normal. So the trend, the red dashed line is a log normal fitted on the data observed on the Lightning Network. Of course, it's not always well fitting the empirical evidence, but still tells you that captures, let's say, some features of the trend. So power law for what concerns the degrees, log normal for what concerns weights and strength. Okay, so let's say, one of the most interesting questions that we asked studying cryptocurrencies is the one about the centralization. So in principle, cryptocurrencies are designed to be decentralized payment system. What about the topological centralization? So in networks, there exist many quantities that try to capture the importance of a node, and these are the centrality measures. What we found is that for the Lightning Network, some sort of centralization is indeed present, however, at a topological level. So although these systems are designed as decentralized payment system, if you look at the network, you find evidence of some structural centrality of nodes. And I will explain what it means. So first, we calculated a kind of topological version of the Nakamoto index. So we said, how many nodes are needed to account for 51% of the total number of links in the network? So how many nodes should you collect in order for their connection to account for 51%? And how many nodes should you collect in order for their weight to be at least the 51% of the network? Now, what we found is that this fraction of nodes decreases with time. So as the number of nodes of the system rises, so the system enlarges, the fraction of nodes that is needed to have 51% of the total number of links and the 51% of the total weight of the network is going down, which means that there are some hub, there is some very important node with many connections and heavy connection that basically sum up a quite large percentage of total number of links and total weight of the network. So we found this decreasing of the Nakamoto index as a sort of indication that some hubs are appearing as the system increases. And then we tried to confirm this intuition by calculating proper centrality indices. In network, you have many centrality indices. We consider these four quantities. For example, the degree centrality. So a node is very central according to this index if it has many connections. Or the closeness centrality. The closeness centrality tells you that a node is very central if it's not so far from all the other nodes. So it calculates the distance, the topological distance a node has with all the other ones. Then you have the betweenness centrality that tells you that the node is central if it's crossed by many patterns. And then you have the eigenvector centrality. The eigenvector centrality is a bit less intuitive, and basically a node with a large eigenvector centrality is connected to other well-connected nodes. It's a sort of PageRank. You have a large eigenvector centrality if you are in a club of nodes which are very well connected and connected between them. We will see better what this means. So in order to understand if there is this centralization, we calculated the evolution of the Gini coefficient of these centrality measures. The Gini coefficient provides a measure of unevenness, so of uneven distribution, for example, of wealth. We again turned into a topological index and calculated it with the centrality measures. Now, the evolution of the Gini coefficient rises. So let's recall that the Gini coefficient is 0 if all the nodes are on the same ground, basically, they have the same wealth. And is 1 if there is a node that has everything and all the other nodes that have nothing. Well, for what concerns centrality, it's going to rise. And it rises for the degree, the betweenness, and the eigenvector centrality. For the closeness centrality, it remains quite stable, and there is a reason, and I will show it later. So the rise of the Gini coefficient tells you that in a sense, the structure is becoming more and more centralized. I mean, the intuition given by the Nakamoto index is now confirmed by these three different centrality measures that tells you that there are nodes that are becoming, basically they are collecting a lot of connections that are in the middle of many paths. The betweenness centrality tells you precisely that. And that maybe are constituting a core of very well connected nodes. And this is what tells you the eigenvector centrality. So the evolution of the Gini coefficient in this respect makes us suspect that something is indeed happening. Now we also asked ourselves, okay, so is the structure becoming, for example, more and more similar to a star? Because if you think of a network structure, the star graph is the most centralized structure that you can imagine, because you have one center and all the other nodes around. So we asked ourselves, is the Bitcoin Lightning Network becoming more and more similar to a star graph, which would signal, I mean, we should be worried, I think, no, from these results. So we calculated the centralization, basically for a star graph, and compared the evolution of this index with respect to the Bitcoin Lightning Network. Now, if the centralization is 1, then the network is a star graph. We can be not that worried, because the evolution of the centralization remains quite stable and quite far from 1. So the network, the Bitcoin Lightning Network, is not becoming like a star graph with one very central node and all the other guys around. However, the Gini coefficient still rises. So how can we reconcile the result from the Gini coefficient that tells you that there is increasing unevenness and the result of centralization that, however, tells you that you are not going towards a star graph? Well, I'm going to show this in a graphical way. So I'm going to show you some snapshot of the Bitcoin Lightning Network by drawing the nodes according to their degree, betweenness, and eigenvector centrality. So here you have two different snapshots. On the left one at the very beginning of the Bitcoin Lightning network history. I don't remember precisely the day. And on the right, some later snapshot. Now, if we draw the size of the nodes in a proportional way to the degree centrality, you see a lot of these center, kind of local star-like structures with these hubs, and attached to these hubs, you have many leaves, many peripheral nodes. They are both present in the early history and in the later version of Bitcoin Lightning Network. What about the closeness centrality? Well, for the closeness centrality, you see that there is not that difference between hubs and peripheral nodes. Why? Well, because a hub is close to all the other nodes, is very connected, so it's also close to all the other nodes. However, if you are a peripheral node connected to the hub, you just need to make one step more to be as close as the hub. So for what concerns the closeness centrality, it doesn't make that difference if you are a hub or a node, a peripheral node connected to the hub. And that's why the Gini coefficient remains quite stable. So the closeness centrality doesn't provide you so much difference. For what concerns the betweenness centrality, instead, you have that the nodes with a very large degree are also the ones crossed by many paths. So you still see these star-like structures around. And for the eigenvector centrality, you have that there is a portion of the network, the central portion of the network, made by very big nodes connected between them. So the idea is that the Bitcoin Lightning Network is not becoming closer to a star graph with a single center and all the other nodes around, but it's becoming closer to a collection of stars. So you have these, locally, you have these hubs that behave like centers of local stars, basically, with some kind of peripheral nodes attached to them. So it's a collection of stars. I mean, you indeed see these hubs that are there. We also made some kind of more refined analysis by finding evidence of a core periphery structure. And we found evidence of a core periphery structure, and the core nodes more or less overlap with the nodes with the largest eigenvector centrality. So even from a statistical point of view, you have this distinction between the central nodes and the peripheral nodes. We also did this from a purely weighted perspective. I skipped the mathematical details, but you can attach a p-value to a partition of nodes. And from a weighted perspective, you see the same. The central nodes, which are the ones gathering the majority of the weight in the network, and all the peripheral nodes that basically exchange much less money, so are in the periphery, are not central. It's interesting that basically, as we see here on the left, the binary and the weighted core for a certain period were basically the same. But now, basically towards the last snapshot of the network, the binary core remains quite stable, and what rises is the weighted core. So what does it mean? That there are nodes with not so many connections that make heavy transactions, that exchange a lot of money. So the size of the weighted core is rising. And let's say there is a kind of overlap between binary and weighted core, or the Jacquard similarity is, let's say, 60%. So there is a superposition of these two kind of course, yeah. So I'm going to conclude. So the idea, I mean, it's interesting to inspect the centrality of these systems, because at the purely structural level, you can indeed recover something that by design should be avoided, which is centralization. And the interpretation that we gave is this one. Why do these hubs form? Because users, when want to pay, want to exchange money, they have to choose a path. Now, the longer the path, the more expensive is the path, because the nodes in the middle of the path basically gain some fee for letting your money pass. So the idea is that if I want to exchange money, I have to find the shortest path. And typically, a short path crosses a very central node. So there is an incentive in creating these central nodes because they let the pattern be less expensive than otherwise. So this can be, let's say, the explanation for this emergence of the hubs. And of course, the presence of the hubs has some consequences on the resilience of the network, because as soon as you remove one of them, maybe because you want to attack them, you disconnect the network very easily. So you remove one of the hub and you have all the peripheral nodes disconnected. So of course, it's let's say it's something that make the fragility of the network rise. So to conclude, basically I have presented an overview of the results of network theory applied to cryptocurrencies, both for what concerns Bitcoin and Bitcoin Lightning Network. One of the most interesting questions, topics that we have faced is that of centralization. And it's interesting to see that, at least to me, that at the structural level, you recover some kind of centralization that in principle shouldn't be there because they are decentralized, they are designed as decentralized payment systems. So that's all. Thank you very much.